You have read about what a collision is. Let's talk about a collision resolution technique called linear probing. For the time being, I'm not going to be talking about separate chaining. Let's look at the diagram at the bottom of this slide. The keys John Smith, Lisa Smith, and so on are going to be hashed into a table. Let's assume John Smith hashes to 152. So we can place John Smith in this position. Lisa Smith, let's assume 001, and we can place Lisa Smith in that empty position. Sam Doe, similar story, let's assume 254. Then comes along Sandra D. It so happens that she also maps to 152. And we have John Smith sitting in this location. What linear probing does with an interval of 1 is that it probes the structure linearly to find the first available empty slot. So we probe 1 down to 153, and this was empty before, so now we can put Sandra D in 153. Ted Baker comes along. Now he maps to 153, but we had just placed Sandra D there, so we linear probe one more time and place Ted Barker in 154. Now that's fine, but what if we're looking for Sandra D? So we take the key Sandra D and hash it, and we get 152. But then we look and we figure out, well, that's not Sandra D, that's John Smith, and if I was going to get Sandra D's number, that's not the right number that I want to retrieve. So understanding what the collision resolution technique in place was, when I find something that isn't quite right, I know how to resolve the issue. In this case, I know how to find Sandra D. I linear probe. In this case, Sandra D was placed in just one position below 152, the original location for Sandra D, and I can successfully find Sandra D. Similar story with Ted Baker. If I were to find Ted Baker, I would hash the key Ted Baker and it would hash to 153. Not finding Ted Baker, I would linear probe until I found Ted Baker. Once again, in this example, we find Ted Baker in this spot immediately following the original position. That's all well and good, but what happens when we delete something? Linear probing cannot exist unless we have the following flags: E for empty, O for occupied, and D for deleted. But how are these flags used? Well, initially, the entire structure is labeled as E for empty. As we start placing items into the structure, we add a label O for occupied. Anytime we remove something, instead of returning the label to E for empty, we replace it with D for deleted. In other words, there used to be something here, but it is now currently deleted. What exactly happens when you're looking for an item when the linear probing collision resolution technique is in place? As we saw, we hash to the location that we think it originally exists in, and linear probe one by one until we find it. In the examples that we've just seen, we had to linear probe a very short distance, but the item was there and we were eventually able to find it. Even if we have to linear probe a little bit of a distance, we'll still eventually find it. Well, what happens when we try to find something that doesn't actually exist? That's a very possible and real scenario. So what happens? We take the key that we're looking for, we'll put it through the hash function, and get a location. We'll discover that either that position is occupied by something else, or that position is empty. Let's start with the scenario that we're looking for something and it hashes to, let's assume, 152. But we're not looking for John Smith. We linear probe to 153. That's not what we're looking for. We linear probe to 154. Ted is also not what we're looking for. We linear probe to 155. And we reach a blank. This would be labeled as E for empty. With linear probing, if you're looking for something and you're probing and arrive at a slot that is empty, you can stop searching at that point. What it means is that the item you're looking for is not there, because if it was in the table, it would exist in that position. So the first empty slot you come across, you can stop searching. That leads us to what happens when we start deleting items from this table. This is where the flags E for empty, O for occupied, and D for deleted, particularly the D for deleted, comes into play. Let's look at this. Let's say we're inserting 52, and it somehow hashes to 2. Well, 72 already exists in that location, so a collision happens. If we're using linear probing, we then probe to 3, well, that's another collision. We probe to 4, that's another collision. We probe to 5, that's another collision. We probe to 6, that's empty. So we can place 52 into that spot. Great, well, what if I delete something along the way? Let's say I delete the item that was sitting in index position 4. I delete 14. Now let's say I want to find 52. Well, 52 hashes to index position 2, but 72 is not 52. We know that linear probing technique is in place, so I start probing. All right, 72 is not equal to 52, so let me probe. 33 is not equal to 52, and let me probe again. Oh, I've reached an empty slot. We come to the conclusion that 52 is not there, but it is if we just probe 2 more spots. But because we came across an empty slot, we stop probing. Now, if we were to employ the D for deleted, so we got rid of the item in 4, but we placed the symbol D for deleted. Same thing, I look for 52 at index position 2, I keep probing till I find it. 72 is not equal to 52, I probe. 33 is not equal to 52, I probe. I hit D. The D tells me there used to be something here, so please step over and continue your search. So I then linear probe one more time. 55 is not equal to 52, I linear probe another time, and I eventually find 52. I am successful in searching for 52. So this deletion anomaly when searching for something can be rectified by the flag D for deleted.